Uh-oh. I got to turn on the machine. Sorry about that. There we go. All right. Quick word about the test. Okay, so the test was fine. Most of you, actually, quite a few of you did better on the second test than the first test. So it looks like the strategy that we adopted of giving you guys more time for the test, that seemed to help. Well, even though the first test, I wasn't even there to monitor, I still gave you, what, an hour and a half pretty much, because I gave it to you at 8 o'clock and you had until 9:25. So you still had an hour and a half. But if you guys want to keep doing the same strategy of whenever we have a test, the next one is what, 22nd, looks like. So we want to make it where I'll do a quick lecture, question and answer is either very short or non-existent, then we can start the test sooner and you have more time. And it seems like having the extra amount of time really worked to a lot of your advantage. Okay. I should have emailed you back the response. I think I did almost all of them on Saturday. I also emailed you the solutions, so I don't have to go over the solutions and waste class time for that. I figured I'll just make a little mini video, and for those of you who want to look at the video, 15 minutes or so of how to get the answers to the test, it was there. Okay, but a lot of you were okay on the test, so maybe on succeeding tests we can do the same strategy. All right. And looking at where we are, I snuck in a little bit of 8.2 last time. I can finish 8.2. I can probably do a lot of 9.1 today already. So it looks like I'm a section ahead. If I can even finish 9.1, I'll be a whole week ahead, according to the schedule. But if not, we'll probably end up finishing early anyway. Okay, so one way or other, I'll either be a whole week ahead, or even if I don't, we'll probably finish a little early today. Okay? So that's what's happening. All right, so back to 8.2. This is on surface area of revolution. Again, we're splitting this next exam up into part of 8 and part of 9. Okay, there's more to chapter 8. There's 8.3, 8.4, and others. There's more to there's more to chapter 9, but this is all that we're required to do. Okay, so we don't have to do 8.3, 8.4. We don't have to do 9.4, and so on. So the next exam will be sort of a combination 8 and 9, and even some of that. Okay. In case you can see, our last exam covers the most amount of stuff. Okay, so there are what, 11 sections, right? So just thought I'd give you a heads up for what that's about. All right, so my goal today is finish 8.2 and maybe start some of 9.1. Okay. Quick reminder where we've been. Okay, so 8.1 was arc length. So arc length formula. Okay, so you want the arc length of a function going from A to B. So you're integrating the square root of 1 plus derivative squared. Integral from A to B, radical 1 plus dy dx squared dx. Or if you have x as a function of y, radical 1 plus dx dy squared dy. Okay, so we were already done with 8.1. Then 8.2, an area of a surface of revolution. So we take a region and revolve it about either the x-axis or y-axis. And you might say, we already did that. Yeah, that time we were doing volume, but now we're doing surface area, just the surface part, if you were to paint the outside of it. Okay, and the basic formula is here on 553. If you want to put it in a cheat sheet, you may notice this is the same as the formula for arc length. Radical 1 plus dy dx squared dx. Or radical 1 plus dx dy squared dy. That's if you have x as a function of y. Okay, so in front you put 2 pi y if you're spinning it about the x-axis. If If you're spinning it about the y-axis, then it's going to be 2 pi x. Okay, and a little bit of notation. Notice this whole stuff here, or this, you can call it ds, which is a tiny change in arc length. So dx, we know, is a tiny change in the x direction. dy is a tiny change in the y direction. ds is along the diagonal. It's a tiny change in the s direction, in the arc length direction. All right. So that's that. And let's see. Yeah, if you're spinning about the y-axis, integrate 2 pi x ds, and ds is either that guy or that guy. You choose for yourself how much do you want to put in your cheat sheet. You can put them all, but that takes up more space. If you kind of got the idea, you say, okay, I got that. If it's dx dy, no big deal. Just change that to dx dy or whatever, right? Spin about the x-axis, 2 pi y. Spin about the y-axis, 2 pi x. You can put them both down, or if you've got the idea, you know that you have that. So notice it's the same formula as section 1, except you have to put the 2 pi r. Basically, you're putting 2 pi r in front, either 2 pi y or 2 pi x. Okay, so last time I only did problem 7, and I'll do a bunch more for you. And again, please notice I adjusted the assignment completely because this was nice for the 7th edition, but this is the 8th edition, 7, 9, 12, 13, 14, 15, 17. I'll do a bunch more from here. Okay. Okay, I was going to show you problem number 12, one of the even ones, 12. Y equals 1/6 x cubed. Yeah, in the book it says x cubed over 6. Why don't I just show you what the book has? X cubed over 6, I'm writing as 1/6 x cubed. 1 over 2x, I'm going to write it as 1/2 x to the minus 1. That's better for taking the derivative, right? And we're going from 1/2 to 1. So the concept is this has some funny shape, okay? And we're spinning it about either the x-axis or the y-axis. In these problems, it says the x-axis. So if you spin about the x-axis, it's going to be 2 pi y. All right, so here we go, dy dx. Derivative of this is 3 over 6, which is 1/2 x squared minus 1/2 x to the minus 2. Okay, this is the Leibniz notation again, L-E-I-B-N-I-Z. The D stuff, dy dx, that's called the Leibniz notation. Leibniz is one of the co-founders of calculus along with Sir Isaac Newton. You don't have to write that down, you don't have to memorize it. Okay, by formula, I'm supposed to square it. So what do I get when I square 1/2 x squared minus 1/2 x to the minus 2? Okay, we have a recurring theme. Mr. Stewart, the author, seems to like this a lot. So I square this, 1/4 x to the 4th. I square this, plus 1/4 x to the minus 4. And then the 2ab term minus 2 times a times b. So 2 times 1/2 times 1/2 is 1/2. 2 times 1/2 is 1. 1 times 1/2 is 1/2. And then x squared times x to the negative 2 is x to the 0. You add the exponents. X to the 0 is 1. So again, you just have minus 1/2 in the middle. And once again, by formula, you're supposed to add 1. If you add 1 to all of this stuff, all that happens is negative 1/2 changes to positive 1/2, right? 1 plus dy dx squared is all of that. And that refactors back into the exact same thing as this, except there's a plus. So it's 1/2 x squared plus 1/2 x to the negative 2 squared. And you can confirm that if you were to square this back out, you get all that stuff. We saw that in section 1, right? Mr. Stewart seems to like a lot of these kind of problems. All right, so we're ready. So the surface area, SA, surface area, integral from 1/2 to 1 of 2 pi y, and here's y, right? The original function, 2 pi y. And then square root of blah, blah, blah squared. We know the way that works. You just cross off the square root and cross that out. So it's going to be 2 pi outside from 1/2 to 1. 1/6 x cubed plus 1/2 x to the negative 1 times 1/2 x squared plus 1/2 x to the negative 2 dx. Okay. And let's see. What am I doing here? Yeah. Okay. In section 1, I did a lot of et ceteras, but I figured, okay, I'll keep going for this one, especially with all the messy fractions. Okay, I could distribute as it is, but I don't like all these fractions, so I'm going to do a little trick. Okay, I'm going to multiply this by 6 to clean this up, multiply this by 2 to clean this up, and then outside multiply by 1/12. So that's legitimate. Okay, I want to get nice numbers. So if I multiply this by 6 and multiply this by 2, I get rid of all this fraction. So ultimately, inside I multiplied by 12. So that means I'm going to divide by 12 outside. Okay, so that gives me pi over 6 outside. Okay, so that gives me x cubed plus 6 times 1/2 is 3x to the negative 1. And both of these halves are gone, so x squared plus x to the negative 2. Okay, so now it's FOIL. This times this, x to the 5th. X cubed times x to the negative 2 is x to the 1. That times that, 3x. That times that, 3x to the negative 3rd. All right, and these two look like 4x, x plus 3x. All right, so we're finally ready. So outside I have pi over 6, 1/2 to 1, x to the 5th plus 4x plus 3x to the negative 3rd dx. Okay, so it's some messy stuff. Okay, so here we go. X to the 6th over 6, 4x squared over 2, that's 2x squared. 3x to the negative 2 over negative 2, and we're going from 1/2 to 1. Okay, and I decided to clean that up before I plug in. Leave that alone, leave that alone. Minus 3 over 2x squared. X to the negative 2 on top means x squared in the bottom, and I'm going from 1/2 to 1. Okay, and unfortunately I reached the bottom on my paper, so I got to go back up. But I'm going to plug in 1 here, here, and here. And then I'm going to plug in 1/2 here, here, and here. Okay, so I get this mess. So pi over 6, 1/6 plus 2 minus 3/2. If I put 1 here, here, and here, I basically just have the coefficients, right? So 1/6 plus 2 minus 3/2. And then if I plug in 1/2 here, here, and here, it's this mess. 1/2 to the 6th over 6 plus 2 times 1/2 squared minus 3 over 2, 1/2 squared. Okay. So how did I clean this up? I got a common denominator of 6. So 1 over 6, 2 is 12 over 6, 3 over 2 is 9 over 6. This, okay. So the numerator is 1. 2 to the 6 times 6 is 384. Okay. 2 to the 6 is what? 2, 4, 8, 16, 32, 64. And 64 times 6 is 384. 2 times 1/4, 1/2 squared. 2 times 1/4. Okay, and I don't like that 1/4 there, so I decided to multiply top and bottom by 4. So this gives me 12 over 2, which is 6. Okay, so trying to clean this up. 1 plus 12 minus 9 comes out to be 4. 4 over 6 is 2/3. Okay, minus, leave that alone, and we said this is 6. So a real weird common denominator now is 384. So that means I have to multiply this by 128 over 128, minus that, minus 1/2. To get to 384, I multiply by 192. 6 over 1 multiplied by 384 over 384. It's just arithmetic. But in case you're wondering, do I have to do this? Yes, you should do this. You can all do arithmetic. Okay, so 256 minus 1 minus 192 plus 2304. Okay, and all of this comes out to be 2367 over 2304. Do some cancellation, do some cancellation. So the best final answer, 263 pi over 256. Okay. All right, 14 is a little different. X equals 1 plus 2y squared. So this is x is a function of y. It says y goes from 1 to 2. X equals blah, so x is a function of y goes from 1 to 2, but you're still spinning it about the x-axis, which means you're going to integrate with 2 pi y. So dx dy for y. 1 plus dx dy squared, that's pretty easy. It's 1 plus 16y squared. All right, and yeah, let me show you how easy this becomes. Okay, if I'm integrating, if I revolve about the x-axis, I'm integrating 2 pi y, but this time we're integrating dy, so I don't have to change this over. Now, the previous problem, when I did 2 pi y, right, I had to change this into an expression involving x because it was dx. But this time, it's more convenient, since you have x as a function of y, this is going to be dy. I can just leave this as 2 pi y. I don't have to change that to anything. I'm integrating with respect to y. So it's perfect. And radical 1 plus 16y squared dy. Okay, so I take out the 2 pi. And notice this is 1 plus 16y squared, whose derivative is almost y. Almost, quote unquote, meaning it's missing the 32. But we know that's not an issue. Okay, so let u be this. This is a regular u substitution. U equals 1 plus 16y squared. Du is 32y dy. There's a y. There's a dy. I'm missing a 32. You can always put a constant in and take it out. So 32 here, 1 over 32 here. So that means in front, I got 2 pi over 32, which is pi over 16. And now y goes from 1 to 2. So if y goes from 1 to 2, what happens to u? Figure out from here. Okay, so y equals 1, put a 1 there. 1 plus 16, 17. Plug in 2 right here. 2 squared is 4. 16 times 4 is 64. Plus 1 is 65. Okay, notice when you change the limits, you can have a very different integral. The original was just 1 to 2. Okay, no big deal. But now we're going from 17 to 65, which is a difference of, what, 48 or something like that. So by changing the limits, you could have quite a dramatic effect on, what you're integrating now. Okay, so pi over 16. I'm no longer going from 1 to 2. That was for the old variable y. Now that I'm in u, because of this relation, I'm now going from 17 to 65. Of radical 1 plus 16y squared is now radical u. And 32y dy. 32y dy, that's my du. And we're home free, just about. So u to the 1/2 du, recurring theme. This happens a lot for these kind of problems. Integrate. U to the 3/2 divided by 3/2 means times 2/3. And a little bit of cancellation here. 2, 16, that gives me 8. So 8 times 3 is 24, so pi over 24. Plug in 65. 65 to the 3/2. Plug in 17. 17 to the 3/2. And I've already told you how I want you to write it, right? So 65 radical 65 minus 17 radical 17. Okay, so once again, don't leave any answer for me as something to the 3/2. We change it like this. Okay, so 65 to the 3/2, 65 radical 65. 17 to the 3/2, 17 radical 17. it's the idea of simplification. Okay. Oh yeah, there's a pi over 24 in front. Okay. Again, the idea is which is considered easier, this or this. And simplification, you're thinking in terms of the general population. Okay, just not calculus 2 students, but picking students, not even students, people at random. Do more people understand this or this, right? I would say there's a lot more people who understand this. They might be kind of fuzzy on square roots. Okay, 65, square root of 65, I can punch that in the calculator. I know what that means. But many, many fewer people know what that means, right? Which you now know that. Again, why are they equivalent? This is 65 to the 1. This is 65 to the half. Add the exponents and you get 3 halves. All right, so again, ground roots for me, and this happens a lot in sections 8.1 and 8.2, as you can tell by the formula, because it involves square roots. So when you integrate a square root, right, you're going to end up with this 3 halves stuff, and so it stands to reason you're going to get a lot of 3 halves, right? So 10 to the 3 halves, 10 radical 10. X to the 3 halves, x radical x. Okay, so that's our ground roots for how that works. Okay, I'm going to show you 13 star. Sorry, it's not in the original. It was in the 7th edition. This is not our 13. It was in the old edition. Okay, but it illustrates a key point because you're revolving about the y-axis this time. Okay, so I'll show you this. So go ahead and put it down, or it's in the video anyway. So you won't find this in the book unless you have the 7th edition, but I needed to show you. So now we're rotating about the y-axis. So I'll show you 2 problems where you revolve about the y-axis, and then I'm done with the section pretty much. So y equals cube root of x. Y goes from 1 to 2, and it says you're integrating with respect to the y-axis. Okay. And I guess the closest problems like that are here. There are only a few problems like that. Okay, the given curve is rotated about the y-axis. Find the area of the resulting surface. Okay, so you know you're going to integrate 2 pi x. All right, so y goes from 1 to 2. Here's a picture. You don't really need the picture, but x is equal to y cubed. Okay, what I need to do was cube both sides, right? Since I'm integrating with respect to y, x is equal to y cubed. And you're going from y equals 1 to y equals 2. Here's my delta y. So spin it about the y-axis. Okay, so x equals y cubed. Notice before I started, I had to cube both sides. All right, so dx dy is 3y squared. 1 plus the derivative squared. 1 plus dx dy squared is 1 plus 9y to the 4th. Okay, so 1 plus dx dy squared. That goes underneath the square root. Okay. So already, if I'm integrating, or it's rather spinning about the y-axis, it's 2 pi x. So here we are, 2 pi x. But what's x? Y cubed. I have to change it to y cubed because I'm integrating with respect to y. And then radical 1 plus dx dy squared, 1 plus 9y to the 4th. Okay, take out the 2 pi, similar theme. Okay, I notice this is y to the 4th, this is y cubed. Perfect. Perfect for substitution. Because you know the derivative of this is essentially this except for a constant, 36. So let that be u. U is 1 plus 9y to the 4th. Du is 36y cubed dy. There's the dy. There's the y cubed. 2 pi joins the 1 over 36 in a second. But yeah, we're missing a 36. So no big deal. Put 36 here. 1 over 36 here. So 2 pi joins the 1 over 36. That's going to be pi over 18 over here. Okay, so one more time. The derivative of 1 plus 9y to the 4th is almost y cubed. That told me to do a u substitution. I need a 36. No big deal. Put the 36 here. 1 over 36. Now I substitute. That's going to be radical u. And now there's my 36y cubed dy. 36y cubed dy. Pretend you erase that replace it with du. And now my limits. Y goes from 1 to 2. What happens to u? Plug in here. So when y is 1, 1 plus 9 times 1 to the 4th, which is 1, 10. Plug in 2. Oh boy, 2 to the 4th is 16. 9 times 16 is 144, plus 1 is 145. Okay, notice the big change. Originally, we were integrating from 1 to 2. Now we're going from 10 to 145. That's just the way it works sometimes. All right, and the rest of the problem is fairly ordinary. So the integral now becomes 2 pi over 36 is pi over 18, right? Integral from 10 to 145 of radical 1 plus 9y to the 4th is radical u. 36 y cubed dy du. And now the rest is pretty much the same as before. So pi over 18. So that's u to the half, recurring theme. U to the 1/2 becomes u to the 3/2 times 2/3. Again, some cancellation. Let's see, 2, 18, that's 9. 9 times 3 is 27. So pi over 27. Plug in 145. 145 to the 3/2 minus 10 to the 3/2. And we know how that works. Pi over 27. 145 radical 145 minus 10 radical 10. And that's my final answer. Okay. All right, then finally 17, and I was going to be done. I would have been done with 8.2. I think I've done 1, 2, 3, 4. I've done 3 or 4 of them, so you don't have to do that many others. And then I'm ready to start some of 9.1. Okay, so 17. Here. X equals radical a squared minus y squared. Y goes from 0 to a over 2. Okay, so we're spinning about the y-axis. You have to pretend a is a constant. Okay. It turns out that a is the radius, okay, of a circle. If you did a little bit of algebra, this is x squared plus y squared equals a squared. So the radius would be a. But just treat a as a constant. Okay, and you're going from 0 to half of a, and you're spinning it about the y-axis again. Okay. All right, so let's see what happens this time. dx dy. Okay, so pretend that this is blah, blah, blah to the 1/2. I'm not writing it, but I'm going to make the assumption you know it. You're in Calc 2, so you already know that stuff. It's blah, blah, blah to the half, right? So the derivative is 1/2 a squared minus y squared to the negative 1/2. Then by the chain rule, it's times the derivative of the inside with respect to y. If a is a constant, that means a squared is a constant. Its derivative is 0. The derivative of negative y squared is negative 2y. Okay, so one more time. This is a squared minus y squared to the 1/2. So the derivative is 1/2 a squared minus y squared to the negative 1/2. And then times the derivative of the inside. Derivative of a squared is 0. Derivative of that is negative 2y. Okay, that 2 is going to cancel that 2. So I have negative y. This junk here to the negative 1/2 means put it in the denominator as a square root. So radical a squared minus y squared. So this is dx dy. X is a function of y. Okay, now by formula, I'm supposed to square it. So dx dy squared, very conveniently, the minus is gone when you square it. The square root is gone when you square it, right? So that's nice. So one more time, you're squaring it. Lose that. When you square a square root, it just drops out. So I have y squared over a squared minus y squared. Is that okay? And now by formula, I'm supposed to add 1. So here's 1. Do you agree that's 1? A squared minus y squared over a squared minus y squared. That's to get a common denominator. Plus dx dy squared, right? It's supposed to be 1 plus this. So I'm writing 1 in this fashion so I can get a common denominator. Okay. And notice very conveniently on top, y squared cancels out. So now I just have a squared on top. So that's 1 plus dx dy squared. That goes underneath the square root in the formula. All right, so now we're ready. Look at how nice this becomes. The surface area is the integral from 0 to a over 2 of 2 pi x. This is x. But I don't write x. I'm integrating with respect to y. So I need to change x to a function of y. So radical a squared minus y squared. And then the square root of this stuff. Square root of a squared over a squared minus y squared. And look at this. Very conveniently, that square root cancels that square root. And what's the square root of a squared? A. So the only thing I have left is 2 pi a that I'm integrating. So integral from 0 to a over 2, 2 pi a. 2 pi a is all constant. You can take the whole thing out, and you're integrating 1 dy. All right, so 2 pi a, integral of 1 is y from 0 to a over 2. Plug in a over 2, I get a over 2. Plug in 0, I get 0. So that 2 cancels that 2. So final answer is pi a squared. And that's it. Okay, so this problem's actually finished, but I'll dig a little bit deeper. I'm only going to talk very superficially about this. You could extend this to an entire circle, which this is not. But if you extend it to an entire circle and spin about the y-axis, so you'll be going from what, negative a to a, you would find the surface area of a sphere. Okay, so you would end up doing the same thing, and you would end up with 4 pi a squared, which essentially means the surface area of a sphere, which you may have heard before, is 4 pi r squared. Okay, so we took a semicircle and spun it about the x-axis. We found the volume to be 4/3 pi r cubed. In fact, you guys did it on a quiz. Okay, and you can do the same thing as I did over here with the entire circle. For the surface area, the formula turns out to be 4 pi r squared for the surface area. So if you were to paint the outside of a sphere, the outside of a ball, where the radius r, that's the surface area of a sphere, 4 pi r squared. Okay. So that's that. Okay, folks, so I'm actually done with an 8.2. So check this off. I'll start some of 9.1. What time is it? Okay, it looks like we have the best of both worlds. I can sneak in quite a bit of 9.1, and we'll probably still finish early today. Okay, unless you have questions, but we'll see how that goes. Okay, I mean, according to schedule, I wasn't supposed to do 9.1 until next Tuesday. So if I can do 9.1, we're a whole week ahead. Okay, but again, I'd rather do it that way in case something goes wrong, my internet goes down, I get sick, or whatever, any of those things might happen. Okay. All right. So what's chapter 9 about? Well, I'm not sure if I showed you all the problems again. So yeah, let me do that again. For those of you that don't have the book and you're never getting it. 8.2, page 555. So 8.2, there's the bottom. Whoops. And there's the bottom. I'm going to move it more centrally. Okay. So if you want to catch this on the recording later. And let's see, we only had to go up to 17. So yeah. So here you're spinning about the y-axis. I made it my own 13, and I actually did 17. So the only one you have to do here is 15. All right, so that's that. All right, so a little bit of introduction to 9.1, and then we'll break maybe a little bit after 8-ish. Okay, so chapter 9. The topic is differential equations. Page what? 585. Okay, so 9.1, 9.2, and 9.3 are all on differential equations. Okay, we're just really scratching the surface of differential equations. Okay, now a lot of you probably know you can take an entire course on differential equations. In fact, most community colleges, the highest course you can take is differential equations. Well, unless you take the course that combines linear algebra and differential equations. I highly suspect many of you have to end up taking differential equations eventually, right? After you finish the calculus series, then you have linear algebra, differential equations. So you can take an entire semester of differential equations. We are just scratching the surface. So we're really just doing the very baby stages of differential equations, right? So 9.1, 9.2, 9.3, you'll learn just the very beginning stages of differential equations, but it's an introduction. So at least when you take a course in differential equations, which I know a lot of you guys have to take, at least it's not totally foreign. You say, okay, I saw it a little bit in my Calc 2 class. Okay, so that's what's happening. Okay, so 9.1 says modeling with differential equations. The first thing that you might want to say is, what are differential equations, right? What is the scary topic, differential equations? Okay. So let me show you what some of the homework problems look like. Okay, so what do we have on the homework? Let's see, 1 through 7 all, ALL, except skip 6B and 7A. And sorry, I forgot to check if that matches in the 7th and 8th edition. I think it does. Anyway, here it is. So page 590. And yeah, for the benefit of those of you that don't have the book and don't plan on getting it again. So here we are, page 590. Okay, so that's 1, 2, 3, 4, 5 maybe. And then up to 7. And here's the rest. Okay. All right, so by way of introduction, differential equation. Take a look at this thing. Y prime plus 2y equals 2e to the x. That's a differential equation. 2y double prime plus y prime minus y equals 0. That's a differential equation. 4y double prime equals negative 25y. Y double prime plus y equals sine x. Okay, so what is a differential equation? Well, let's just break it down. Equation, so you learned in Algebra 1, what's an equation, right? There's an equal sign, there's a left-hand side, and a right-hand side. So whatever a differential equation is, first and foremost, it's an equation, right? Equation means there's an equal sign, right? Equal sign, equation, equal sign, equation, equal sign, equation. By the way, this is also an equation. It's not a differential equation. These are equations. It's not a differential equation. This is an equation. It happens to be a differential equation. So we know equation means there's an equal side, there's stuff on the left, and there's stuff on the right. All right, so we got equation. Now, can you guess what differential means? There's derivatives. Okay, so differential equation is simply an equation. There's an equal sign. And either the left side or the right side or both have some derivatives in it, right? Like this, y prime. Okay, y prime means derivative, right? So, and there's an equal sign. So differential equation. There's a derivative, and it is an equation. There's an equal sign, right? 2y double prime. So yes, you're allowed to have second derivatives, third derivatives, whatever. 2y double prime plus y prime minus y equals 0. There's the equation. There are derivatives, right? Here's the equal sign, so it's an equation. There's a double prime, so derivative, differential. Differential equation. There's an equation, equal sign, and there's a derivative, y double prime, or whatever. Okay? So differential equation, very simply, is an equation that has one or more derivatives. Okay? So what's involved with these differential equations? So granted, right now we're at a very, very low-level baby stage of differential equation. Okay? Most of this is what I call show and tell. You don't have to write that down, but show and tell says show that blah, blah, blah works. Show that y equals whatever is a solution of the differential equation. Okay, so here's a differential equation, right? Y prime plus 2y equals, can't even read it, 2e to the x. It's an equation and differential. There's the equation part. There's the derivative part. Okay. Right now, we don't know how to solve any of these. Okay. When we get to 9.3, we'll learn how to solve some very elementary differential equations. Okay. Show that this is a solution. Show and tell. Okay. So we're not ready yet to ask, how did you come up with that? Okay. Well, I'm not going to ask any questions, right? We don't know how they got that. Just plug it in, and what do you know? It works. Okay. The very, very baby stages of differential equations. Okay. Maybe the best thing I can say by analogy, think back to your algebra 1. Okay. If I said 2x equals 4, right? 2x equals 4, all of you can say, oh yeah, x equals 2. Okay. But before that, even before that, suppose I said, show that x equals 2 is a solution to 2x equals 4, right? So show it works. Okay, I just plug it in. Plug in 2. 2 times 2 equals 4. Hey, what do you know? It works. Okay. How did you get it? I don't know. I just plugged it in. They told me to plug it in. It works. Later on, you learn techniques, right? Like if I said 2x equals 4, then you say, oh yeah, divide both sides by 2. Okay. We're not even at that stage yet. Okay. So the very, very baby stages of 2x equals 4, they tell me, okay, plug in 2. How did you get to 2? I don't know. Just plug it in. Oh, okay. Told me to plug it in. I plug in 2 times 2 equals 4. Hey, it works. Okay. That's the level that we're at in 9.1. Show that this works. You're saying, where did you get that from? Don't ask that yet. Okay. Just plug it in. Hey, it works. I have no idea how you got it, but it works. Okay. 2x equals 4. Plug in 2. How did you get that? Don't ask right now. Just plug it in. Well, okay. Plug it in. It works. Okay. Plug this in. Show that it works. How did you possibly come up with that? I don't know. Don't worry about it. Just plug it in, and what do you know? It works. Okay. So that's the very elementary stage we are right now. Here's a proposed solution. For 9.1, we're not going to ask, how did you get that? Okay. We're not going to learn that. In fact, for this particular equation, in my class right now, Calc 2, you're never going to learn how to do this. Okay. You'll learn this if and when you have to take a course in differential equations. Okay. Well, obviously, there must be more techniques to this. In general, solving differential equations are not that easy. I mean, there must be obvious reasons. Why do you take a whole semester, right? You can take a whole semester in differential equations, where the whole semester is nothing but this stuff. For us, it's just going to be what? 9.1, 9.2, 9.3, just 3 sections, right? As opposed to taking a whole semester of differential equations. Okay, so we're going to take this equation. You say, how did you get it? Don't worry about it now. Just take y prime plus 2y and see if you don't get 2e to the x. Okay, same thing here. Same thing for a lot of these. Okay. So t dy dt, we know that means derivative. Y equals y plus t squared sine of t. Y of pi equals 0. Here's something extra. It just means when you plug in pi, you get 0. Show that's true. Okay, so we're going to plug in pi here and here and here, and supposedly you get 0. So we'll see if that indeed comes out to be the case or not. Okay. All right, so let me try to show you number 1, and then maybe we will break. Okay, so differential equations. Y equals that is a solution to y prime plus 2y equals 2e to the x. So again, that's just like saying 2x equals 4. Plug in 2. How did you get that 2? Don't ask. Just plug it in. Right? So it's like same thing. How did you get that? I don't know. I'm just going to try it. And what do you know? It works. Then, of course, later you learn techniques. Like when I say 2x equals 4, all of you can say, oh, yeah, divide both sides by 2 and get that. But even before that, the very baby stage of algebra, 2x equals 4. Plug in 2. Okay, plug in 2. 2 times 2 is 4. It works. Okay, so plug this in. Where did you get it from? Don't ask right now. We're just going to try it. All right, so let's find y prime. So what's the derivative of this? So the derivative of 2/3 e to the x is the same thing. Derivative of e to the negative 2x is e to the negative 2x times negative 2. So I have this. That's y prime. Okay, now I find out y prime plus 2y. Now, when you're doing this proof, you must not put 2e to the x yet. Okay? We're trying to show it's 2e to the x. So if you put y prime plus 2y equals 2e to the x, you're already assuming what you're trying to prove. Okay? In logic, that's called circular reasoning. If you're trying to prove it, you don't assume that it's true. So I make no assumption that this is true. Instead, I write down y prime. Here it is. And then I put plus 2y, right? So here's y prime, 2/3 e to the x minus 2e to the negative 2x. Here's 2y. Y is the original function, 2/3 e to the x plus e to the negative 2x. I work this all out. Okay, so I work it all out. 2/3 e to the x minus 2e to the negative 2x. And then 2 times that is 4/3 e to the x. And that's 2e to the negative 2x. Okay. And lo and behold, these two cancel out. 2/3 e to the x plus 4/3 e to the x is 6/3 e to the x, which is 2e to the x. What do you know? It works. That's the end of the proof. Okay, and sometimes you'll see me do this, the double line, the double slash. That's actually in logic, that means end of proof. Okay, that's what was to be proved. Okay, so we're done with the problem. They said show and tell. Show that it works. I have no idea how they got that. We don't care right now. I plugged it in, and what do you know? It works. Show and tell is done. Show that this works. How did you get it? I don't know. I plugged it in. It works. Okay, I did y prime. Here it is. And then they wanted me to do y prime plus 2y. All right, here's the y prime. Here's 2 times the original y. Grind it out. What do you know? 2e to the x. Okay. All right, so that's that, folks. Let me stop the share, check the chat. There's nothing in the chat. Okay, so we'll take a break. All right, so let's see, a little bit after 8:15. Okay, so let's start again at 8:15, please. All right. Okay, folks, 8:15, so we'll go ahead and get started again. Let's see, I think I'm caught up with the chat, so we'll get back to where we were. Okay. All right, so we're doing differential equations. I did problem 1. I'll do several more. And let's see. So the game plan now for Thursday is it looks like I'll go ahead and do some of 9-2. I'm quite a bit ahead, so if I don't do that much, that's okay. I'll leave enough time for the quiz. Okay, I was planning for the quiz to be on 8-1 and 8-2 material. So quiz would be on arc length and area of a surface of revolution. So maybe I'll give you one of each, let's say. Okay. And the way I do the quizzes, of course, is, I would say don't even study it carefully or hard. I mean, again, you'll be in your breakout groups, you'll get to talk about it, and then you have the whole weekend to submit it. It's not due until class begins next Tuesday anyway. All right, so for this semester at least, I try to make my quizzes very low pressure. Okay, so I'll do 9-1. If I don't finish 9-1 today, that's okay. I'll start some of 9-2. Schedule-wise, I think we're okay, unless, again, something goes wrong, like my internet goes down or I get sick or whatever. Okay, and then I'll leave you enough time to get started on the quiz. So let's just aim for 8.1 and 8.2. Okay, so arc length, surface area revolution for the quiz on Thursday. So right now I'm thinking in terms of one question each, one from here and one from here, perhaps. That's not a promise. I'm not guaranteeing that, but that's what I'm leaning toward for the quiz. Okay. All right, so I'll try to do a bunch more from 9.1. 1 to 7 all, skip 6b and 7a. Okay, number 2. Y equals negative t cosine t minus t. Is it a solution to the differential equation t dy dt equals y plus t squared sine of t? And this time they're telling you y of pi equals 0. Okay, so they give you this extra piece of information. Okay, so here's a differential equation. How do I know it's a differential equation? There's a derivative, and it's an equation. This is an equation, but not a differential equation. Okay, so it looks like our solutions are functions. Okay, and there's this extra information, y of pi equals 0. Okay, that's actually the easy part. Plug this in. Okay, sometimes this is called an initial condition. Initial condition. We'll learn more about that in a future section. Okay, that part's easy. Plug in pi, you get 0. Okay, plug in pi there, there, and there. So y of pi is equal to, that should be equal there, equals negative pi cosine pi minus pi. Put a pi there, there, and there. So negative pi cosine pi minus pi. Cosine of pi, 180 degrees, is negative 1. So I have negative pi times negative 1 minus pi, which becomes pi minus pi, which is 0. Okay, so end of that proof. So that part's easy. Okay, the initial condition is usually the easy part. The harder part is all this stuff. Okay, so I need dy dt. So first find the derivative of this. Okay, so for this part, it looks like product rule, right? First function, second function. So negative t, first function times the derivative of the second. Derivative of cosine t is negative sine t. Plus the second function, cosine of t, times the derivative of the first. Derivative of negative t is negative 1. That's the product rule from Calc 1, you might recall, right? First times the derivative of the second, negative t times negative sine t, plus the second function, cosine t, times the derivative of the first, negative 1. And the derivative of negative t is negative 1. Okay, so clean this up. Double negative, so t sine t minus cosine t minus 1. Okay, so all of this is dy dt. All right, now I figure out t dy dt. I figure out y plus t squared sine t, and hopefully they're equal. Again, I make no assumption that they're equal. I do them separately. So first figure this out, separately figure this out, but you don't say this equals that. That's what you're trying to prove. Okay, so that's circular reasoning. You don't prove it by assuming they're equal. I make no assumption that these are equal. I just work this out. I separately work this out, and then I'm going to show that they're equal. All right, so here we go. T times dy dt. T times that stuff. This was dy dt. Okay, then you just distribute. So t squared sine of t minus t cosine of t minus t. And hopefully that's the same thing as the right-hand side. So here we go. The right side is y plus t squared sine of t. So y plus t squared sine of t. Y is just the original function. So I copy that, negative t cosine of t minus t plus t squared sine of t. And comparing this with this, what do you know? They're the same. There's t squared sine of t. It's not the same order, but you already know addition is commutative, right? You can change the order. A plus B plus C is the same as B plus A plus C, which is the same as C plus B plus A, right? You can mix them up. So that equals that matches that, and that matches that. So end of proof. They certainly are equal. Okay. And notice in this very baby stages of differential equations, okay, we don't know how to answer. How did you get that? In other words, suppose I started off with this, right? You said, here's a differential equation. Solve it. Right now, we have no idea how to do it. Okay. Here's a solution. How did you get that? Don't ask. Right? Don't ask. Just show that it works. No, okay. I have no idea how you got it, but I did it. It works. So there it is. And by the way, when you come up with a solution, there's no guarantee that this is the only solution, right? We know that, especially in algebra, you could have many solutions, right? Or even in trig, right? There are many solutions. So all we're saying is that this is a solution. Is this the only solution? We don't know. Maybe there's more. All I can say is this definitely is a solution. Why? I worked this out. I worked this out. I have no idea how you got it, but they're equal, so it definitely works. Okay, 3 is a little bit different. Let me show you the wording. For what values of r does the function y equals e to the rt satisfy the differential equation 2y double prime plus y prime minus y equals 0? So it's a little bit of an attempt to solve. Okay, find a value of r, or find values of r, so that e to the rx satisfy this differential equation. So find r. Okay, so in other words, is it going to be 10x? Is it negative 3x? Is it pi x? Is it a million x? Right? What r values will make this work? So this is our first attempt to sort of solve a differential equation, and I'll show you how to do that now. Okay. So they give me y equals e to the rx, and here's a differential equation. Find values of r which make it work. So here's what you do. I need to find out y prime and y double prime. So what's the derivative of e to the rx? Remember, r is considered a constant. So the derivative by the chain rule is the same thing, e to the rx, times the derivative of rx, which is r. So I have r e to the rx. Remember, r is a constant. Y double prime. So what's the derivative of this? R e to the rx. Well, it'll be r e to the rx. And again, times the derivative of rx, which is another r. So it's going to be r squared e to the rx. Okay, so here's my y prime, y double prime. Okay, so one more time. The derivative of e to the rx is r e to the rx. It's just like saying, what's the derivative of e to the 2x? It would be e to the 2x times 2. What's the derivative of e to the 10x? E to the 10x times 10. So the derivative of e to the rx is e to the rx times r. And if I differentiate again, Again, I get r e to the rx, and then by the chain rule times another r, so r squared. Okay, so this expression goes right there. This expression, y prime, goes right there, and y is just that. So 2y double prime plus y prime minus y, this stuff, is 2r squared e to the rx. Okay, this stuff right here is y double prime, right? Plus y prime, there it is, minus the original y, equals 0. Okay, so I have that. Okay, there's a common factor of e to the rx. So factor out e to the rx, 2r squared plus r minus 1 equals 0. Okay, you're looking for a value of r, which will make this 0. This can never be 0. We already know that e to anything is always positive, so that can't happen. I just solved that, and that's just some simple algebra. Factor into 2r minus 1, r plus 1. So by the 0 factor property, I'm going to have 1/2 or -1. Okay, so these are my r values that work. So I have y equals e to the half x, or y equals e to the negative x. Okay, so that's the answer to the first part. So the values of r are 1/2 and -1, which means e to the half x and e to the negative x supposedly work. Okay, the next part of the problem is even more. For those values of r that we have, show that every member of the family of functions y equals a e to the r1x plus b e to the r2x is also a solution. So what does that mean? Okay, so we have our r1 and r2. That's like r1 and r2. What they're saying now is this: let a and b be any real numbers, coefficients. This will be a solution to the differential equation. A e to the half x plus b e to the negative x, which incidentally also shows you, like you might say, well, can you prove that that works and that also works? Well, this sort of does it. We're going to prove it works for any real number a and b. So it works for any real number a and b. E to the half x is put 1 here and 0 here. If this is a 1, this is 0, you have e to the half x. And e to the negative x would be putting a 0 here and a 1 here. Okay, so if I prove it works for any a and b, then I've proven it works for e to the half x and e to the negative x also. Okay, so supposedly you put in any real number for a, any real number for b. So in other words, you have infinitely many solutions. So I could put here 40 million e to the half x minus 316.521414828 e to the negative x. That's going to work. Okay, so how do you do it? Show and tell. Okay, so here's proposed solution for any a and b plugged into 2y double prime plus y prime minus y. Okay, so what's y prime? What's the derivative of a e to the half x? A e to the half x times a half. What's the derivative of b e to the negative x? Negative b e to the negative x. Again, it's a chain rule. Right? You would multiply it by -1, so there we go. So this is y prime. Now I want y double prime, so I differentiate this. So what's the derivative of this stuff? Well, it'll be the same thing, 1/2 a e to the half x, and then by the chain rule times an extra half. So I have half times a half, which is a quarter, 1/4 a e to the half x. And what's the derivative of negative b e to the negative x? It switches back to positive b e to negative x. Because again, by the chain rule, the derivative of this would be the same thing times -1. So if we multiply by -1, that minus changes to a plus. So here's y double prime. All right, so here we go. 2y double prime. I'm putting it back into here. So 2 of this thing, here it is, 2y double prime. So I'm just copying that, plus y prime. So here's my y prime. I got it from here. minus the original y. So minus this. If it's minus this, they're both negatives, right? Minus parentheses. So negative a e to the half x minus b e to the negative x. Okay, I claim this is 0. Okay, let's see if I can prove that this is 0. Okay, let me look at like terms. E to the half x. Here, here, and here, right? So that's 1/2 a, right? 1/2 a plus 1/2 a. So what's 1/2 a plus 1/2 a? 1a minus a. So that's 0. Okay, so again, half a e to the half x plus another half a e to the half x is 1 a e to the half x minus a e to the half x is 0. And now the e to the negative x is that one, and that one. Okay, so I have 2b minus b minus another b, 0. 2b e to the negative x minus b e to the negative x minus another b e to the negative x is 0. Okay, so it works. Okay, so I've proven that we actually have an infinite class of functions. Give me any real number you want for a, any real number you want for b, it's going to satisfy this differential equation. Okay, and oddly enough, even though I say that, okay, this sounds weird, this is a property of infinity. Even though we have infinitely many solutions, we have not proven that that's all the solutions. Okay, there's infinitely many, but that's maybe not all of them. Maybe there's some other functions that don't look like this that make this work. Okay, so we don't know that now. So you see, differential equations is quite a rich field. We're only learning very little. We're doing, what, 3 sections out of our book. But again, many of you have to take an entire course in differential equations. The whole semester, can you imagine doing a whole semester of equations that look like this, right, that have derivatives in them? So that's just a little foretaste of what it's going to be like when you take differential equations for those of you that have to take differential equations. Okay. Next one I want to show you is number 5. I wasn't going to do all of it, but I'll give you enough of it to see what you have. There's an A, B, C, D. So let me show you what it's about. (5a). Which of the following functions are solutions of the differential equation y double prime plus y equals sine x? So they give you 4 proposed solutions. Y double prime plus y equals sine x. So y equals sine x, y equals cosine x, y equals that, or y equals that. So your answer is either going to be yes or no, but don't just put yes or no on the homework or the quiz or test. You actually have to work it out. In other words, find out y double prime, plug it into y double prime plus y, and see does it come out to be sine x. That's all. Okay, so each one has an answer of yes or no, but I'm not going to accept it if you just say yes or no. You got to show me, the second derivative and plug it in. Okay, so I decided to do A and D for you. You do B and C on your own. Okay, so y double prime plus y equals sine x. So the first proposed solution is sine x. I mean, that's logical. I mean, if you wanted to equal sine x, maybe say, well, let's try sine x, right? And let's see if it actually works. So y double prime. So if y is sine x, y prime is cosine x. Y double prime is negative sine x, right? So that's my second derivative. Okay, now I plug it in. Y double prime plus y. So y double prime was negative sine x plus the original y is sine x. Negative sine x plus sine x is 0, and that's not equal to sine x. So no good. The answer to A is no. It does not work. Okay, and then letter D says y equals negative a half x cosine x. And yeah, you might be saying, this is so weird, okay, or follow the logic, I guess. Okay, we tried sine x. I mean, that seemed very plausible. Okay, sine x, here it is. Even though this was a plausible guess, it didn't work. Okay. And now for D, I'm showing you this one. This looks so weird, which leads you to believe maybe it is going to work, right? If you're following that logic. Of course, that's not a proof, but let's see if this weird thing actually satisfies a differential equation. Okay, so negative a half x cosine x. So product rule, first function, second function. Okay, y prime first times the derivative of the second. So negative a half x times the derivative of the second is negative sine x, plus the second function cosine x times the derivative of the first. Derivative of negative half x is negative a half. Okay, clean it up. Two negatives make a positive. 1/2 x sine x minus 1/2 cosine x. Okay, so that's my y prime. Y double prime. So I differentiate this. This is another product rule. Well, let me get this out of the way. What's the derivative of negative a half cosine x? Positive a half sine x, right? Because the derivative of negative cosine is positive sine. Okay, so the derivative of negative a half cosine x is plus a half sine x. Okay, now let me focus on this. So first function, second function. So the derivative of this is first function half x times the derivative of the second, derivative of sine x is cosine x, plus second function sine x times the derivative of the first, derivative of half x is a half. Yes, I know some of you put the chat. I can't see the chat right now until I stop share screen, so I'll get to it eventually, hopefully. All right, and I clean this up. That's half sine x plus another half sine x. That's just sine x. And so I have half x cosine x plus sine x. All right, so here we go. Y double prime plus y. So 1/2 x cosine x plus sine x. And then plus the original y minus 1/2 x cosine x. What do you know? It comes out to be sine x. So this one's a yes. Okay, so especially for differential equations, looks can be deceiving. Right? What was a very good guess, you say, oh, there's a sine x, maybe I'll try sine x. It didn't work. But something which seems totally weird, okay, to make it look like that, it actually does work. So we got what we wanted for that one. Okay, let's see, 840. Okay, I'm just going to do a couple more. Let me go back and check the chat quickly, please. Okay, the updated homework for 8.1. So 8.1, 1, 2, and 7 and 19 odd. So a lot of you guys already had that. So 8.1, 1, 2, 7 through 19 odd. Let's see. The 7, 9, 12, 13, that's for the 8th edition. Okay, so 8.2, 7, 9, 12, 13, 14, 15, 17, or you can see it's in the chat. Those are the problems from the 8th edition. Okay, and let's see, I think I'm caught up with the chat. All right, so I'll switch back. Now, sorry, I can't seem to do the share screen and the chat at the same time. Go ahead and put something in the chat, but I won't be able to get to it until later. Sorry about that. Okay, 6 and 7, and then I was going to be done, folks. So 6 has A, B, C, D, skip B. 7 has A, B, C, D, skip A. Okay, and let me show you why. Now, 6B has a graphing calculator icon, so that's why. So we're going to do 6A, C, D. And 7 What can you say about a solution? Okay, I don't even know what they're asking there. So yeah, we're going to forget 7A. What can you say? I don't know. What can you say? You can say anything. So we'll just do B, C, D. Okay. All right. And here's the language again. Initial condition. I wrote it in the notes, but y of 1 equals 2 or y of 2 equals 1, those are called initial conditions. All right. So 6A, show and tell. Show that y equals blah, blah, blah is a solution of differential equation. Okay. And then what's going to happen for C and D is we're going to be able to solve for C. All right. So let me show you that. Okay, y equals ln x plus c over x. First thing I want you to notice is the way they write it. Okay, we're used to having blah, blah, blah plus c. This is not algebraically the same. The plus c is all in the numerator. In other words, it's not like this. It's not ln x over x and then plus c like we're used to. It's ln x plus c, the whole thing divided by x. And mathematically, it's not equivalent. Or you could think of it this way. You could split it into two, right? You could say ln x over x plus c over x. So that's not the same as what we're used to, blah, 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 and then over here plus c, right? So plus c is part of the numerator. All right, show and tell. Show that this satisfies this differential equation. How did you get that? I don't know. Don't worry about it now. Just show that it works, right? Just like my 2x equals 4. Plug in 2. How did you get that? I don't know. I just plugged in 2. 2 times 2 equals 4. What do you know? It works. And then later on, much later on, you learn how to solve algebraic equations, and much later on, you learn how to solve differential equations. Okay, so first let's find a derivative. So quotient rule. Okay, so bottom times the derivative of the top. Derivative of the top is 1 over x. Derivative of any constant is 0. Minus the numerator, ln x plus c, times the derivative of the denominator, derivative of x is just 1, all over x squared. Okay, quotient rule. Right, remember the quotient rule? It's the bottom times the derivative of the top minus the other way around. Top times the derivative of the bottom all over the square of the denominator. Okay, so clean that up. That's 1. Well, if we multiply by 1, forget about it. So 1 minus minus. So 1 minus ln x minus c. Okay, so this is my y prime. All right, so now I plug in x squared y prime plus xy, right? Notice again, I do not put equals 1. You're not supposed to put equals 1. That's what you're trying to prove. If that's what you're trying to prove, you don't assume it. Okay, so I'll put x squared y prime plus xy. I make no assumption that it's equal to 1. That's what I'm trying to prove. Okay, so x squared times y prime. Okay, so here's my y prime. So x squared parentheses, all this stuff, plus x times the original y. So there's the original y. I put that right there. Okay, and you'll notice it's very, very nice for this differential equation. X squared happens to cancel out. X happens to cancel out. So I got no more denominator. So I have 1 minus natural log of x minus c plus natural log of x plus c. ln x cancel, c cancel. What do you know? It's 1. It works. How do we get it? I don't know. Right now, I don't care. Okay. They said show that it works. It works. If it's written in this form, again, so watch out. The plus c is not hanging off to the side like we're used to. It's all in the numerator. Okay. Now, what's this c and d stuff? Y of 1 equals 2. That's called an initial condition. It just means when x is 1, y is 2. Plug it in, figure out the c. Okay. So for these initial conditions, y of 1 equals 2, that means x is 1, y is 2. This means when x is 2, y is 1. If you forget which is which, kind of cover this up. It looks like y equals 2, right? So that tells me, okay, y is 2, that means x is 1. And likewise, when it says y of 2 equals 1, if you cover it up, it says y equals 1. So that tells me, okay, y is 1, that means the other letter, x, has to be 2. So all that's going to happen is you plug in the x, you plug in the y, you can find the c. So you have a specific function, not infinitely many functions, right? This is infinitely many functions that differ by a constant, but we're going to be able to find the c. Okay, so plug in x is 1 right here and right here, and y is 2. So 2 equals ln 1 plus c. ln 1 turns out to be 0. So the right-hand side is just c over 1, or c. So c is 2. So just put the 2 here, and you're done. So y equals natural log of x plus 2 divided by x. So this is not infinitely many functions like this one is. It's only one function. This one function has two properties. Property number 1, this thing satisfies this differential equation. Property number 2, when you plug in 1, you get 2. And do the same thing for 2 comma 1, you might just have a different c. Okay, so y of 2 equals 1 means plug in x equals 2, y equals 1. So back up here, put a 2 there, a 2 there, and a 1 there. And it looks like this. Okay, solve for c. Multiply both sides by 2. Subtract ln x. So c is equal to 2 minus natural log of 2. That's a weird number, but it's a number nonetheless, right? You can punch it in your calculator, like 1.3 something or whatever. Okay, so that goes right into c back at the beginning. So final answer, y equals natural log of x plus 2 minus ln 2 all over x. All right, number 7, folks, I'm done. We got plenty of time. All right, so it looks like I got the best of both worlds. I think I'm going to finish early, and I'll be completely done with section 9.1. How do you like that? So if I look on the schedule, I wasn't supposed to finish 9.1 until October 13th. This is October 6th. So I'll be a week ahead, which means I'm not planning on doing this, but I can, quote unquote, afford to. Again, I'm not going to do it, but I can afford to skip a whole week, and we'll be back on schedule. I'm not going to do it. I don't know what's going to happen. We don't know what's going to happen. So I'd rather just keep going ahead, as the case may be. Okay. So that means next time, yeah, I'll sneak in some of 9.2, but make sure you have enough time to do the quiz, which is just on the 2 sections, 8.1 and 8.2, right? Arc length and surface area of revolution. Okay, so number 7, let me show you the wording again. So it never mattered about A. A was a skip. B, verify all members of the family. Verify is the same as show. So you can say show that, verify that. All members of the family y equals 1 over x plus c are solutions of the differential equation y prime equals negative y squared. Okay, and I'll come back to C in a second. And then D has an initial condition again. All right, yeah, so we can knock all of these off. I would have done at least half the problems, I think, either a half or maybe even more than half, but even if I'm a little bit less than half, it's quite a bit towards your required 70%, right, that you know how to do these. Okay, I'll come back to C. All right, so y equals 1 over x plus c. Again, please notice the way they have it. It's not, 1 over x and then plus c, like we're used to. The plus c is part of the denominator. Okay, so they're not mathematically equivalent. Okay. Now, I could do the quotient rule, but I'd rather not. It's way easier to think of it as x plus c to the negative 1. Okay. Generally, if you have a constant in the numerator, I would avoid doing the quotient rule. Okay. Quotient rule is one of our least favorite, right? What is it? Bottom times the derivative of the top minus the top times the derivative of the bottom, all over the denominator squared, right? Okay. You try to avoid that if possible. So x plus c to the negative 1, way better. All right, so y prime, negative 1, x plus c to the negative 2. Then by the chain rule times the derivative of the inside. Now remember, c is a constant. So if c is a constant, the derivative of the inside is just 1. Okay, so I have negative 1 over x plus c squared. All right, and now let me figure out negative y squared. That's very easy. So it's the negative of the original squared. Negative 1 plus x, 1 over x plus c squared. That's negative 1 over x plus c squared. Hey, they're the same. They are definitely equal. Okay. So how did you get it? We don't know yet. Okay. We'll learn a little bit more in section 3. Okay. We will actually solve some differential equations of a very particular type. Okay. It's called separable equation. Don't worry about that now. And you don't even have to write it down now, but I'm just letting you know. There are certain types of differential equations called separable equations, and we'll see that when we get to it. But there it is. I figured out y prime. It's the same as negative y squared. Notice I didn't show you how to solve this. Okay? We're just saying, here's a proposed solution. How did you get it? I don't know. I don't care. I just did that. I did that. It fits a differential equation. Okay. Part C is a little bit weird. I already showed you the answer maybe, but can you think of a solution of the differential equation y prime equals negative y squared that is not a member of the family in part B? In other words, it doesn't look like this. Okay. That actually is pretty simple. Okay. I've already shown you the answer, but pretend I didn't. Y prime is negative y squared. Okay. The easiest function you can think of is y equals 0. Okay. What is the derivative of 0? 0. What is negative 0 squared? 0. So y equals 0 definitely works. Okay. But y equals 0 doesn't look like this. You can't make it look like this. Okay, so here's an example of, okay, we have infinitely many functions here. Just give me different values c. So 1 over x, 1 over x plus 1, 1 over x plus 2, 1 over x plus 3, 1 over x plus 80, 1 over x minus 80, 1 over x minus pi over 2, 1 over x minus a billion. They are all solutions of this differential equation. Okay, so, but even though we have infinitely many solutions, that's not all of them. Okay, and I know that sounds like a contradiction, but here it is. Here's another solution which doesn't look like this, but it's also a solution. So just because you have infinitely many solutions does not mean you actually have all of them. So y equals 0 works. Okay, part D, and then I'm done, folks. I'll be done in just a few minutes, and it's not even 9 o'clock. Okay, so I'll be done in a second. So if you want to ask me questions in probably 2 or 3 minutes, you can send it through the chat now, or you can unmute yourself at that point. But if nobody has any questions, we can finish early. That's up to you guys. Okay, so think if you want to ask any questions, we may, but if not, we can just call it a day. So now for the last part of 7D, find a solution of the initial value problem, y prime equals negative y squared, y of 0 equals 0.5. Okay, that's just like C and D. Okay, let x be 0, y be 0.5. Again, if you forget which is which, cover that up, and it says y equals 0.5. So that tells me, okay, that's y, so that means that must be x. Okay, if I plug in, I'll be able to find a particular value of c. So instead of having infinitely many solutions like this, I'll be able to plug in the x and the y and find just one particular solution because I'll be able to find what c is. Okay, so when they write y of 0 equals 0.5, plug in x is 0 right there, y is 0.5 right there, and it looks like this. 0.5 equals 1 over 0 plus c. 0.5 equals 1 over c. So c is equal to 2. Okay. Not sure if you've seen this trick before. When you have something like this, you're allowed to just swap these two. Put the c here and the 0.5 here. So 1 over 0.5 is 1 over 2. Okay. One thing that might be obvious if I plug it in, 1/2 is the same as 0.5, right? So you know that works. Okay, but a little trick, you're allowed to just swap these two. Okay, So C equals 1 over 0.5. 1 over 0.5 is 2. So just plug that in for C right here. So I have 1 over x plus 2. Okay. So I'm done with that, but let me blab a few more seconds and then I'm done. Anytime you have something like this, you're allowed to just switch these. C equals B over A. You see how I just swapped these two? Okay, what's the justification? Well, you can multiply both sides by C. I'll just talk about it, I won't do it. If you multiply by C, that gets rid of that. You have AC equals B. And then just divide both sides by A, and you have that. Okay. It becomes very obvious when I put in real numbers. Like, here, let me show you this. 5 equals 15 over 3, right? And what do you get when you switch them? 3 equals 15 over 5, right? So we know that works. So maybe that'll help you in solving some equations. Anytime you wish, when you get something that looks like this, you can just swap these two. Just put the C here and the A here, and it works. Okay. All right, that's all that I have for today, folks. So before I get rid of that, I am now completely done with 8.1. Okay, so I can get started with 8.2 next time. Oh, sorry, 9. I'm completely done with 9.1. Okay, so I'm up to here. So again, next time, 9.2. I'm not sure if I'll finish it. I can slow down a little bit, give you the quiz, second half on 8.1 and 8.2. All right, so let me stop the share. 9 o'clock now. Okay, so check the chat. And I don't see anything else in the chat. Okay, so you can ask questions, either unmute yourself or put it in the chat. But if not, we can just call it a day and we're done.
Could you go over number 6C, part C and D again?
6C and D?
Yes.
Okay, want to look at that again? Okay, you can do that. It's basically just plugging in. Whoops. Okay, 6C. So we've already done with this. So y of 1 equals 2 means all I do is I plug in x is 1, y is 2. So this is what I had, right? Y equals ln x plus c over x. So just put the 1 in for x, the 2 for y. And just solve for c. Came out to be 2. Same thing for d. This one says plug in x is 2, so put a 2 right there. Y is 1, put a 1 right there. Solve for c. Came out to be 2 minus ln 2. So that weird number I put back into here. Okay.
Okay. Thank you.
You're welcome. Okay, let me check the chat again. No quiz today, right? Quiz on Thursday. Quizzes are usually on Thursdays, if anything. Got that. Okay, I think I'm caught up. All right, anybody else want to ask a question, please? Give me a moment. You can either unmute or put it in the chat. Okay, I don't hear anything. I don't see anything in chat. So we're done, folks. Okay, so we're done. Good night. So next time, be ready for the quiz. You don't really have to study. So it'll be on sections 1 and 2, right? So the arc length and area of the surface of revolution. Okay. All right, that'll be it, folks. So have a good night. See you next time. Bye, everyone. Thank you.
Bye, Mr. Hom. Good night.
All right, thank you. Good night. Bye. Bye.
Good night.